Alrighty, so we'll be taking a look at the question pretty quick. Before we get to that, I actually stopped at the library yesterday. I went to the front desk and I asked them if they had any books on paranoia. And the librarian told me, they're right behind you. I asked the librarian if they had any books on paranoia. The librarian told me, they're right behind you. Because that's kind of like... Anybody know why the ocean, this is kind of a science question, why is the ocean blue? So it reflects off the atmosphere, and because the sky is blue, the ocean is blue. Good guess. Not what I'm looking for, though. The ocean is blue because the shore never waves back. Poor ocean. All right. There have been worse jokes than those, so you're welcome. Let's take a look at the question here. So this is about space, and it's about Pluto. So we've been talking about Pluto quite a bit in astronomy lately, whether or not it should be a planet. Most people think it should, including myself. It's kind of fun then because if you're going to say that, you have to then just actually back it up, because you have to then define what a planet is. So then the question is, how would you define a planet? It's a fun little rabbit hole to go down and see if people would actually define a planet the way that would include Pluto or not. It's interesting to do. But anyway, Pluto is way out there in space. It's a long ways away. And there's an asteroid in that area, and it's flying towards the Earth at a very high speed. Does it have more potential energy, or does it have more kinetic energy? Any thoughts on this? Kinetic. I hear one vote for kinetic.
Actually, they're the same, because that's how it usually is.
Okay, they could be the same. I'll tell you this, it's one or the other. So how many people would vote for this asteroid, which is relatively large, moving very quickly, to have greater kinetic energy? Raise your hand. Okay, that's a good amount of people. How many people would vote for it having a larger potential energy? Because it has a large mass and it is a long ways away. That would be a few less, and that's okay. So let's take a look and see what this would give us here. We actually don't need numbers to figure this out. So as I mentioned, kinetic energy is 1/2 mv squared. So an asteroid is a rocky body in space that usually has a good amount of mass. They can range from a couple of feet across to hundreds of miles across. The largest one, Ceres, is about 600 miles across. So big mass, moving quickly, so it's got a big velocity. So absolutely, it does have a large kinetic energy. Let's take a look at potential energy. So that's mass times g times height. So it does have a large mass, and it is definitely a long, long ways above Earth. It is far out there. This g value, though, is a little bit interesting. Anybody, bless you, who voted for kinetic energy being bigger, anybody want to comment on this g value at all? Yeah. So because we are further away from the Earth, this g value gets smaller and smaller. So we use it as a constant of 9.8 because that is what it would be on the surface of the Earth. But the further you get away from the surface of the Earth, the smaller this value is going to get. So by the time you get out by Pluto, your gravity from Earth is non-existent for all practical purposes. So, because that's a very small thing for this asteroid, indeed the answer is kinetic energy. That would be the larger of the two here. And we'll talk about that a little bit more when we get to orbital motion near the end of the school year. So, let's do some review for the test tomorrow. I have a feeling you guys are going to be rather confident by the end of this session. All right. There's the information I'm going to give you. Calculate potential energy, please. You have 30 seconds.
Whoa, chill.
It would be helpful to have your formula sheets up. Yep. All right, that's long enough. So when you look at your formula sheet for potential energy is just equal to mass times g times height y. So it's just a matter of plugging those into that equation. 10 times 9.8 times 4 is going to get you an answer of 392 joules. 392. Questions on this one? This is the kind of stuff you'll find on page 1 of the test, which happens to be multiple choice. This one's going to take a little bit more thinking. So we found our final potential energy equal to 392. Let's say this object, which is falling, ends up hitting a spring. That spring has a spring constant of 50. So now my question is, how far is it going to compress that spring? So the object is falling from a great height, 4 meters, and it encounters this spring. How far will it compress? Give you a little bit more time on this one. Yes. 30 seconds, finish up.
Well, it's only like 2, no, it's a lot of weeks after I figured out I don't, it's 3 weeks after, because this, we're going to win the first one, probably lose the second one. He said we can be up for the
All right, what'd you get for this one?
X equals 5.
Good guess. Yes.
X equals 3.95.
3.95 or 3.96 would be good answers for that, absolutely. So let's take a look at this one.
Yeah, I tried.
So one of the biggest things you'll be doing on this test is using the conservation of energy. You set all your energy at the beginning equal to all your energy at the end. So here, you begin with just potential energy. At the end, once the spring is fully compressed, you will have transferred all that to spring potential energy. So all we're doing here is we're going to be setting the original potential energy equal to the final spring potential energy. Now we know that we begin with 392 joules. Spring potential energy is 1/2 kx squared. So the k is 50. And then we've got x squared. So now it's just a little bit of math. We got to get this x by itself. So 1/2 times 50 is 25. And in order to get this 25 out of here, we got to divide both sides by 25. And that's equal to x squared. So what do we do to get rid of the square? Square root, absolutely. And that gets rid of the square there. And when you do that square root, you should get about 3.96, 3.95, something like that. Yep. And that's going to be in meters. Always remember, too, that you have to keep these units in meters. These were all given to you in meters and seconds and kilograms, but always be on the lookout if you have units that are not those. Always make sure you convert to seconds, meters, and kilograms. Questions on this one? Okay. Let's talk about pies.
Cherry?
Yeah, we can do cherry.
I actually don't like cherries.
I'm sorry to hear that. Should we do a different color?
Blueberries.
Blueberries? Okay.
I hate apples.
Blueberry.
You don't like apple pie? I don't like warm fruit. I think it's just bleh. It's like I'll eat peach cobbler, but just the cobbler, not the peaches. Do you know what that is, Alexa? Because Jolly asked me what's that. I just wanted to make sure.
Okay. So this is an object. You let it go from up here. It travels down. And I want you to make some energy pies out of this. We need some energy blueberry pies. Go ahead and do that. Also do the energy bar graphs.
So is, for the bottom one, is it on the ground or just above the ground?
It's just barely above the ground. The moment before impact. I know, it's a long time ago, and it's very different from the last two worksheets. But just like I've said in the past, just because this stuff is straightforward doesn't mean it's not going to be on the test. It's going to be a fair amount of this. Just about one full page is dedicated to it. So if you had a good time with it, look forward to page 2 of the test. 4. Like 2 pages, 4 sides. No. Finish this up, 30 seconds or so. If you've got some spare time, throw in the energy flow. We'll talk about that too. Yeah. Okay. What is all the energy in the first blueberry pie?
Potential.
Very good. What about the second?
Potential and kinetic.
Very good. And the third? Yeah. Excellent, excellent. Of course, you always have the option of making this pie into a planet. So, what is the original energy then for the first bar graph? Potential, absolutely, because that's what we begin with. And then because it's all kinetic at the bottom, your final chart would look like this. Nothing too terribly difficult, hopefully. If we're talking energy flow, we begin with potential energy. And then for a while, we have both potential and kinetic. And then at the end, it is all potential.
Kinetic.
Oh, yeah. I mean, I was testing you. Good job.
For the test, do we have to write it in the circles, or can we like write it to the side?
You can write it to the side,
Okay.
as long as I can tell what you're saying.
Okay.
So that's the first one. Let's do another example of this, because as you probably guessed, we are going to have at least one on there that includes energy either being lost or gained. So we'll do that one now. All right. Let me tell you a little bit about what's happening here. We've got a car that is at the very top of this hill. I want you to do a pi for when it's up there. And then I want you to do a pi for when it's right here, halfway down. At the bottom, this is where a couple interesting things take place. At the bottom here, it's moving its absolute fastest. So do a pi there. Right after this point, we could say right here, the brakes are applied and it comes to a stop. So give me the energy right after it comes to a stop there. So 1, 2, 3, 4. Also do your bar graph and your energy flow. Take your time on this one. Finish this one up in the next minute. All right, so let's take a look at this. What kind of energy does this object have when it is at the top of a hill? Potential, yep. Now it's rolling down the hill. It's about halfway down. What's the energy? Yep. At this point, before the brakes are applied, we are at the bottom. So what's the energy here? Yep. And finally at the end, when it is at rest after the brakes have been applied. This one's going to be nothing, because if there's no velocity, it has no kinetic energy. If it is on the ground, there's no potential, and there's no springs around, so there's no spring potential either. So that's what we have for the pies. For the original and final bar graphs then, the beginning is all potential energy. The end is nothing because there's nothing left. Energy flow, let's take a look at this together. At the top, it does have all potential energy, so that's a good place to start. Now, if it just started rolling down on its own, you could go straight to potential / kinetic. But if it says that the object has to, do a little bit of work, or maybe the engine needs to be on and you need to start idling towards the edge of the hill, if that's the case, then work would come next. And on the test, it'll be specific about these things. So when it starts rolling down then, and it has both potential and kinetic, we'll have both of those. And then it gets all the way to the bottom. So then it only has kinetic energy. And finally, it comes to rest. Where did all that energy go? Heat. Precisely. And what letter is heat? Yep. So Q would be the last thing on your energy flow there. And that's the sort of thing you'll find on page 2. The last 2 pages make use of the equations in more depth than the first page, because the first page you will have to use them, but the answers are in multiple choice form. So page 3 and 4, you're going to have to do some actual work with these without the possible answers in front of you. So let's put a scenario up here. Take your time on this one. So here's the setup. You've got a mass that's 500 kilograms. A force of 300 newtons is being applied to it. And as that force is being applied, the object moves 20 meters. My question to you here is, how fast is the object moving once it reaches this 20 meters? So we're solving for the final velocity here. What is the velocity once this object reaches 20 meters? You're going to need some energy equations to figure this out. I'll give you about 5 minutes or so, maybe closer to 4, so that we have time for the last one or two. But take your time on this one. Don't rush it. See if you can find that velocity. One minute. Finish on up. All right, anybody confident enough to share their answer here?
4.9.
4.9 is right on the money. Anybody else get 4.9? Very good. All right, so let's take a look at this one, if you didn't end up landing there. So we are looking for velocity. So what that basically means is somehow we're going to have to use kinetic energy, because that's the only energy equation we have that actually has velocity in it. So we're going to end up hopefully there somehow. Now we don't have enough information to find kinetic energy right off the bat so that we can solve for this, because we don't know what that velocity is. So we got to set that kinetic energy equal to something that we do know. There's nothing up here for potential energy, because we're not off the ground. We're just going across it. There is no spring involved here, so there's no spring potential energy. So what does that leave us with? Marta? Work, precisely. So when we're talking about work, remember it's equal to a couple different things. Work is equal to change in energy, and it's equal to force times distance. So we've got force and we've got distance here. So this is a problem where we're going to be using work and setting it equal to change in energy in order to figure this out. More specifically, change in kinetic energy. So we've got a force of 300. We've got a distance of 20. And then, we're going to set that equal to our change in energy, 1/2 mass, which is 500. Velocity is going to be equal to what we're looking for. And then, of course, we'd subtract from this the original kinetic energy. Well, the original kinetic energy is 0 because the original velocity is 0. So this is the only equation we need to deal with. So 1/2 times 500 is 250. So we gotta, and this times this is going to be 6,000, I think. So that'll be 6,000. Divide both sides by the 250 is equal to velocity squared. Square root both sides, and that's what should get you your velocity of 4.9. Very good. Let's do another one kind of like this. All right. So we got to throw something in here with power. We have a mass of 500 kilograms. Original velocity is 1 meter per second. Final velocity is 5, and it takes 3 seconds to go up from 1 to 5 meters per second. How much horsepower is being used in order to accomplish this? So I'll tell you this much. Once you get your power, you have to divide that power by 746. And that gets you your answer in horsepower. So take just 60 seconds or so to get as far as you can on this one, and then we'll go through it together. Yes. Okay, that probably wasn't enough time to get too far, but I want to make sure we can cover this. So if we're looking for power, remember that power is simply equal to your work divided by your time, which is the same thing as your change in energy divided by time. So we got to ask ourselves, do we have enough information for any of the three kinds of energy here? The answer is, of course, yes. We've got mass, we've got two velocities, so that's enough information that we can find out change in kinetic energy. So that's exactly how we're going to tackle this. So it's going to be equal then to our change in kinetic energy divided by time. So we've got 1/2 mv squared and remember, when you're doing change in, it is final velocity here, minus original, final kinetic energy minus original kinetic energy. And then we got to divide that by time, which is 3 seconds. That'll give us a total power of 2,000 watts, if done correctly. And, of course, then, to translate this to horsepower, we divide by the magical number of 746, giving us a horsepower of 2.68. That would be our answer here. With the last 60 seconds, I just want to mention you will be using a couple of these motion equations. Now, for the part on the test where you're going to be doing this, it's kind of a longer problem where you need one answer to do the following parts. So, you know, you need part A to do part B, you need part B to do part C, and so on. So here's what I want to say about this right now, and I'll mention this tomorrow too. If you cannot figure out the answer to part A, you need to just set the answer to part A equal to something so that you can do part B. If you can't figure out part B, set that answer equal to something so you can do part C. You will not lose points if you do part C correctly, but you didn't do part B correctly. So just wanted to give you a heads up on that. See you tomorrow. Study up. If you have questions, let me know. I'm here before and after school if you want some extra practice. See you later.